They're like surviving school. Yeah.
So we have a question from the photoelectron spectroscopy review, number 20. So this is the PES review, number 20. Which peak is generated by, oh no, sorry, I'm reading number 19. Compared to a 3p peak in the PES chart for phosphorus shown above, a PES chart for sulfur. So this is phosphorus. Ooh, I don't like these ones. They're confusing to me because they start here. You'll notice that this one starts at 0. We have 1s. Why is this small? Why does it start at? Oh. Hang on. Okay, hang on. I think this one goes backwards. Oh, this is very confusing. Let's just skip yeah. Okay, so this would be 1s2, and this is 2s2. This one goes backwards. This makes me very unhappy. I'm going to have to go back and switch these all around. Okay? This would be 2p6. This would be 3s2 and 3p3. Okay, now I know why they were causing problems this morning. I apologize for that. So if you're doing anything in here, just bear in mind that they might be backwards. And they might also be like chopped in half and put one on top of the other. Because really, what should happen is we should chop. Hang on one second. Let's see if I can do this. Print screen. Okay, let's take this and let's stick it in a Word document. Okay, and then we're going to take this one. Where is it? And we're going to stick it in a Word document. Okay. We're going to make them both smaller. La 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 la. Wrap text in front of text. Wrap text in front of text. Make it smaller. There we go. And we're going to take this thing and we are going to flip horizontal. And we're going to take this one and we're going to flip horizontal. Okay. So, and we're going to crop this one here because this is useless. We don't need any of that. So really what this should look like is like this, except for they should be attached. Okay. Right? So it should be, we would have a break along the axis here. Why will you not stay? I don't know. Anyway, we would have a break. So we would have the 1s2, the 2s2, 1s2, 2s2, 2p6, 3s2, 3p3. So that's phosphorus. Okay? So what they are asking then, and I think this is going to be problematic because it's backwards, so maybe we should just skip this question, but we'll answer this one. Okay? Let's see. Oh, not that one. Here we go. We want to know sulfur should have a 3p peak. Now, if we compare where sulfur and phosphorus are, phosphorus is 1 to the left of sulfur. So what's different about phosphorus? Will it have the same height of the 3p peak or a different height? It'll have a different height. Will it be higher or lower? Phosphorus is to the left of sulfur. So sulfur is going to be, it won't be 1s2, 2s2, 2p6, 3s2, 3p3. This is phosphorus. Sulfur is to the right of phosphorus, so it will have one more electron. I think I said it backwards over there. Does that part make sense? Sulfur is to the right, so it has one more electron. So that means that our 3p peak will be higher. Okay. So it'll be a higher intensity. And sulfur, in addition to having one more electron, what else does it have? It also has one more proton. So will it be less tightly bound or more tightly bound? It'll be more tightly bound. So it'll have a higher binding energy. So it'll have a higher intensity and a higher binding energy. The answer key says lower? Well, that's just wrong. The answer is B. Yes?
Does intensity just mean height?
Intensity means height, yes. Yeah, yep. So a higher peak and a higher binding energy for sulfur compared to phosphorus.
Sulfur is group 13.
Sulfur is group 16. Phosphorus is group 15. So sulfur has one more proton and one more electron.
Yeah, but if you know one more proton, increase it down to the peak towards the
Yes.
Oh wait, no, that is higher.
Good? Okay, cool. Anyone have any questions from anything else? It can be from the workbook, it can be from problem sets, whatever. Yes? 10.2c. 2D. Yes. Okay. Write an equation representing first electron affinity, that one. So we would have a gaseous neutral atom, because that's what we're always starting with. And we are adding an electron. And we get X minus gas plus the electron affinity. And your question was? Oh, no, it should not say X plus, it should say X minus. Is that better? Okay, cool, thank you. Yes? It means that it's not as close to the nucleus and the charge of the nucleus is less. Or one or the other or both of those two things. Yeah? Did that answer your question? Okay, cool. Anything else? Yes? Will electronegativity be, oh, electron affinity could be, sure. I won't put it in as a big thing, okay? But you should be able to write an equation for it. Do you know what I mean? Like, yeah, you should know what it is and know the general trends. I don't think I'm going to get too excited about it, though. Maybe it won't be there at all. That's just the luck of the draw. I'm trying to combine 2 units without making the test too big. So there's bound to be something here or there that just doesn't end up on the test. So maybe it'll be that. I don't know. Yeah. Anything else? You remind me of me. That's something I would do.
I don't know how to like explain it, but like I have a bunch of stuff labeled here, like an underline, but I don't really remember what was the question. But I had like a bunch of stuff just labeled as ask Miss Spence.
Okay. So this is 10.2C number 2. Okay. Let's go look at 10.2C number. Whoops, sorry. 10.2C number 2.
Does the answer you said in like overall force function power most of electrons smaller?
Let's find out. I'm just going to answer it from scratch. Okay. So the second ionization energy of nitrogen. So nitrogen is 1s2, 2s2, 2p3. So the first ionization energy will take us to 1s2, 2s2, 2p2. Second ionization energy will take us to 1s2, 2s2, 2p1. And the third ionization energy will take us to 1s2, 2s, 2p0. Okay. Why is the third ionization energy harder or higher? Because we have fewer electrons, there's less electron-electron repulsion. If that's not what the answer key says, then tell me to fix it. Is that what the answer key says?
Okay, if there's less ED repulsion, does that mean there's more Coulombic attraction?
Yep.
And then thus the remaining electrons are more strongly held by the nucleus.
Yep.
Because the answer key was says like therefore the overall force probably R most electrons is smaller and well thus requires less energy.
Oh, that's backwards. Fix the answer key. So the more Coulombic attraction. Therefore, electrons are held more tightly. Therefore, ionization energy is higher.
Also, the same worksheets also 10.2C number 4.
Okay, so number 4, we also have an answer key problem.
No.
Oh, just a different question. We'll find out. Perhaps it is another answer key problem. Let's go see. Number 4. We have 6 ionization energies. We have which group in the periodic table does this element belong to? So I am looking for a giant jump, which looks to happen right between 4 and 5. So that means we have 4 valence electrons. Are you guys good with that? 4 valence electrons, which means it will be group 14.
Wait, why can't it be 4?
Why can't it be group 4? Group 4 is a transition metal, and they don't behave in normal ways. I would never ask you about transition metals and their ionization energies. Is that all you wanted to know? Would you guys like an explanation of this, or are you okay? You're okay? All right, good stuff. Anything else? Okie dokie. technically, we still have a little bit left here, but I don't think they're that important when it comes to the AP exam, you know? I mean, metals have low ionization energies. They're over on that side of the periodic table. You should know that. This is page 61. You should know that they're shiny, that they're malleable, and they deform when they're hit by a hammer. They're ductile, able to be drawn into wires. They have high density and are good conductors of heat and electricity. Have you not been learning that since like grade 8, basically 8 or 9? Okay. Solids at room temperature, high melting point, low ionization energies. This is actually something that we will deal with next year. They tend to get oxidized. Oxidized means losing electrons. Losing electrons is oxidation. And there's a little mnemonic we use in grade 12. Leo, the lion, says, grr. So, LEO, losing electrons, is oxidation. So if you have Mg, which is just neutral, if it becomes Mg2 plus and gives its 2 electrons to somebody else, okay, we're not going to write down who at this point, but if it loses 2 electrons and becomes Mg2 plus, that is oxidation. LEO, losing electrons, is oxidation.
So it doesn't have to be necessarily with oxygen.
Doesn't have to be with oxygen.
Like you can have like magnesium.
You can have single replacement reactions or all oxidation reduction reactions. Okay. Let's see. They tend to become ionic compounds. Metallic character increases down a group. Kind of makes sense, right? More metallic. Least metallic. That makes sense, right? Where are your non-metals? They're up at the top there. So reactivity for metals, this is on page 62 now. Reactivity depends on whether the element reacts by losing electrons, and that's what metals do, so that's what we're looking at here. And what is losing electrons? Oxidation. Or gaining electrons, and this is the Leo the lion says grr, gaining electrons is reduction. GER. The opposite of oxidation. So when magnesium loses its 2 electrons, it has to give them to somebody else. The one who gains those electrons gets reduced. As you move from right to left, reactivity increases. Why? As you move right to left, ooh, this is different. Reactivity of metals increases. What do metals do when they react? They lose electrons. Why would they be better at losing electrons as we go to the left?
Obviously, there's more metallic property.
More metallic property, but what is that based upon? The Zeph, there's fewer protons, so they hold their electrons less tightly, so they'll be more reactive. It's easier for them to give away their electrons the further left you go. Yes? For better word for what? Because they have fewer protons and so the coulombic attraction is smaller. No, I mean, you could say the electronegativity is lower and so it tends to hold on to its electrons less tightly. But if you want to get down to the real root of it, it's all coulombic attraction. Yeah? So there's weaker attraction, nuclear charge, smaller. Weaker attraction for the electrons. It becomes less and less difficult to lose an electron. As you go down, what is going to happen to the reactivity? It's going to increase. Why is that? Metals react by losing electrons. And what happens as you go further down the periodic table? More occupied shells, therefore the electrons they are losing are...
Oh, so is that where like the no reaction and reaction, like the part of that comes from?
So yeah, what Tony's talking about, you know that activity chart that you had? Now, there's other factors in there, and when you get into like the transition metals, there's all kinds of weird effects that go on, okay, because nothing's ever nice and normal with the transition metals. But if you go down from like lithium, sodium, potassium, rubidium, cesium, francium, everything gets more and more and more and more reactive because you have more occupied shells. It is easier for those guys to lose their electrons. Yeah? Now, here are some reactions that will not be on your test because I'm looking at your test and I'm like, it's going to be way too long if I put this on your test, okay? But if you stick a metal into water, it will literally become a hydroxide. So if you throw sodium into water, and if I'm really clever, tomorrow I will remember to bring my sodium in from home and we can throw it in some water. Okay, so you can actually see what happens. And we can put some phenolphthalein in there. What color will this turn phenolphthalein if we have hydroxide? What kind of a substance do we have? We have a base.
Strong base.
It's a strong base. And what color would that turn phenolphthalein? Pink. Now, this is an exothermic reaction. So where would our heat term go? Goes on the right side. And do you guys know anything about hydrogen gas, the properties of hydrogen gas? It's not just flammable, it's explosive. So what's going to happen if you combine heat coming out with an explosion, with an explosive gas?
Boom.
Bang. Okay, so tomorrow, I have to clean out the fume hood as well. Send me threatening emails, like, or post on Teams or something to be like, remember to bring the sodium tomorrow. Okay, if I forget tomorrow, we'll do it next week, but I'd like to do it tomorrow for you. Oh, you're not going to be here. Oh, we could do it next week, I suppose. Anywho, I'll try and remember it for tomorrow. Okay. So we have metals. We have metal oxides. And metal oxides, guess what they also form? They form a base, but there's no hydrogen gas. So do you see how the reaction is basically the same, except for there's no hydrogen gas? I don't think you need to know this one. But if you take a metal oxide and you put it with an acid, you'll get a salt and water. Okay? But these two here, they do show up on the AP exam from time to time, and they just kind of want you to know that. Okay? So throw those into your reactions barrel. It won't be on this time's test, but we'll maybe have like a little review of it in the new year, okay? With our new reactions, maybe like a little quiz on it or something, okay? Teach students. Oh, this is just like advice from like AP gods. Teach students that because metals react by losing electrons, a loosely held electron will result in a more reactive metal. This is directly tied to ionization energy. With increased number of energy levels comes an increased distance from the nuclear attraction and thus a more loosely held electron. Did I teach you guys that? Yes. Do not let students say that metals are more reactive at the bottom left-hand corner because they are at the bottom left-hand corner. Okay? Always give an explanation. Don't give me a trend. Here's some practice writing the reactions, which I'm sure you're not interested in because it's not on the test. Am I correct? Figured. Okay. Non-metallic stuff. This is page 65. Non-metals are non-lustrous. They are poor conductors of heat and electricity. They have lower melting points and lower densities. Again, I think this is and they are brittle. The solids are brittle anyway. Are they going to have low ionization energy or high ionization energy? Over on the right-hand side of the periodic table. High. They do not tend to lose electrons at all. Not naturally, anyway. They have high electron affinities. So they tend, if they have a high electron affinity, that means they are good at doing what? Gaining electrons. And what is gaining electrons? Reduction. So here again, we have Leo the Lion says GR, losing electrons is oxidation. Those are our metals. Gaining electrons is reduction. Non-metals. Where do you think the non-metallic character is the highest? Top right. Yeah. Noble gases are their own kind of little weird thing. Least non-metallic. How do nonmetals react? Nonmetals do what? They tend to gain electrons. So nonmetals react by gaining electrons. So as you go towards the more non-metally kind of things, are they going to become more reactive or less reactive? More reactive. Why are they becoming more reactive as we go from left to right? More protons. Easier to pull electrons, higher coulombic attraction, blah, blah, blah. Okay. As we go up a group, what happens? More reactive. Why? As we go up a group, why are they more reactive? There's fewer occupied shells, therefore the incoming electron can get closer to the nucleus, therefore it becomes more stable and will release more energy. Okay. Non-metal oxides. Do you remember what metal oxides did? Metal oxides reacted with water to make what type of solution? Base. Metals form basic solutions when you mix them with water. Metal oxides also form basic solutions when you mix them with water. What do you think non-metal oxides do when you mix them with water? Non-metal oxides don't produce base, they produce acid. Did you have a question, Joanne? Did you have a question? No? Okay. Again, I'm guessing that you guys don't care about this because it's not on your test. So, we'll just leave that. And metalloids, we don't have time to put that on your test either because we don't have enough room we're just going to cover the basic concepts. So I think we're going to leave that for today. And I'm going to give you guys a little bit of time to work on reviews. Yes? Okay. And we're calling that done for Unit 6 and 7. Yes? I will post the reviews on there. Yes.